Hi everyone, I'm Moein, and in this lightning talk, I'm going to introduce our recent work on developing a pre-silicon vulnerability discovery for trusted execution environments. First, I'm going to start with what TEEs are and where they are used. So TEEs are hardware extensions that provide stricter security guarantees for security critical applications. They provide an isolated environment or an enclave that runs sensitive code or interact with the secret data. TEEs have many use cases that include multi-tenancy on cloud, where you don't have to trust the cloud provider, or even you don't have to trust the other users running on the same machine. Other use cases of these may include running cryptography algorithms or DRM on edge devices like mobile phones. So here at this figure, you can see a cloud system where each user is assigned to an enclave, and all enclaves are protected from each other and also from the untrusted hypervisor through hardware-enforced isolation. But since their emergence, TEEs have been targeted by many microarchitectural attacks where the integrity or confidentiality of the victim enclave can be shown to be broken by either a malicious enclave or by the untrusted hypervisor. So that's why assuring the security of TEEs is very important. But many existing works on TEE verification often miss the complex interactions of TEE with the underlying microarchitecture. So as an example of this, a recent effort on formally verifying RISC-V rocket ship PNP checker, which is the backbone of many TEE designs for RISC-V systems, concludes that this implementation of PNP checker passes the verification. But here in this work, we show that the same verified module, if it's used on top of an out-of-order core, it will end up leaking the enclave data to the untrusted world. So that's why we argue that for a complete verification of a TEE design, we need to verify the TEE software and its hardware and also the underlying microarchitecture all together. To that end, we present TEESec as an effort to jointly verify the TEE software and hardware and also the underlying microarchitecture. So the goal is to verify that the data or metadata does not leak outside the enclave. Now, here the challenge is that the enclave data and metadata is pervasive across all microarchitectural elements, and also the underlying hardware is opaque. So to address this challenge, TEESec performs a detailed RTL level verification of a processor's microarchitecture and also its TEE implementation. We have evaluated TEESec on 3 complex out-of-order RISC-V cores, the last 2 versions of RISC-V Boom, and also the second stable version of Xiao Nanho. We also use Keystone open source framework to deploy our trusted enclaves. So using this setup, we've been able to discover 10 distinct security violations on Boom and Xiang. For a deep dive of one of these security violations and also to know more of how our verification framework works, please attend our talk at ISCA Monday, June 19th at 9:30 a.m. Session 1C. Thank you.